Lesson 5.6, analyzing logarithmic functions. This is part 1 of 3 parts for this lesson. The goals for this lesson first is to determine the value of a logarithm using the change of base formula. So that's one of the formulas we'll be applying today's lesson. And the second goal is to sketch a transformation graph of a logarithmic function. So we have done transformation of exponential function, we've done transformation of different kind of quadratics, previous lessons. Today we are looking at sketching the transformation graph of a log function. And your assignment will be from your textbook to check on your understanding. Questions 1 and 3 on pages 402 and 403. And also from your textbook exercises, question 3, 4 on page 405. So the key concept for today's lesson, and these are the 2 concepts based on the 2 goals. The change of base formula can be used to evaluate a log with base other than 10. Now, if you look at most calculators, if not all of them, I mean, for basic calculators, you have a log button here, but this isn't always in log base 10. The question comes up, what happens if you have a calculator, but you need to calculate the log other than base 10. Today, we will be learning about the change of base formula that you could use to evaluate a log with base other than 10. The other concept is that transformation can be applied to a graph of a log function using strategies we have established from graphing functions. So those are 2 main concepts we'll be using and applying. And so at the end of the lesson, you'll be able to apply. This is a change of base log formula. And I'll prove this formula. And then we look at the transformation function of a logarithmic function. And I'll go through this in this lesson. Just a quick review, and we've done this before, but I'll do it again. Comparing log function, right? And this is in your example booklet. Here we have exponential function and a log function. So whenever we look at the characteristics there, we know that the log is the inverse of an exponential function. But I'll focus on the log function in this case here. This is your graph of a log. It has an x-intercept of at 1, so that's your So the graph has an x-intercept at 1, so it's 1, 0. The graph approaches y, but never touches. So your y-axis is your vertical asymptote. So your vertical asymptote is your y-axis. There's no y-intercept because the asymptote is the y-axis. The domain, therefore, is from 0 to infinity. X is greater than 0. And the range, because the graphs start from infinity and going up to negative infinity to positive infinity, the range is all the real numbers. And the function is increasing because as x increases, y increases. So that's a little review of the log, general log function. So we apply this, using this to get our transformation. So have this handy as a reference. Okay, let's look at first. Let's look at the constructor understanding. Let's look at get our little great minds working here. So we want to evaluate log 2 to the 6. The first thing you want to do is to write this step 1. So write log 2 to the 6 in exponential form. So if you write this in exponential form, right? So you're going to assuming, let's say we have log 2 to the 6, and this is equal to x. Then write this as an exponential. We make it into an equation now, a function. Write this as in exponential form. So now it becomes 6 now is equal to 2 to the power of x. Now 6. So this is your base, that's your exponent, 2 to the power. So this is an exponential form. Now, I'll take this and write it as a common log. So take common log for both sides. So this becomes log 6 equals log to the x. Now, for this here, because this is a common log, and this is 10, I should write this as look like a base, but this is 2. Maybe the common log would be 10 base 10. Now we can use the power law. Okay, so we have log 6 equal to x log 2. Remember, this is base 10 now because of the common log. Common log means base 10. Now, we are going to solve for x now. So we divide both sides. So log 2 so what am I left with? X now with a common log, log 6 over log 2. Now this now I could use my calculator. Log 6. So I'll go to my calculator here. I'll be using my log button. Okay. So log 6 divided by, make sure you, whenever you're doing this, you put a bracket around it. divided by log, oops, no, not natural log, 1 log 2. That'll give me a result of 2.5849. So we can say that x is equal to approximately, well, 2.5849 goes on. So now to write this as an exponential form, right? So we have the x, we have that there equals 6. So we can say x here is 2.5849, which is an irrational number. So look at your strategies here. You have a function, an equation, then you change that to an exponential form, take the common log for both sides, solve for x, and then use your calculator for a base 10 in your log. So most calculators have this log button. That's his base 10. By default is base 10. Now, some calculators, you may be able to calculate logs other than base 10. But this is mainly for calculators do not have those functions. Okay, let's go and do that. By the way, in your booklet, you will see it's written in a different form. You'll see it's written as log a to the x. It's the same thing, it would be x over a. Your textbook has log b to bx. So it means the same. So in your booklet, I think one of your booklets is written in this form. And this would be log x over log a, and you have the base here. It's the same. So it's a matter of labeling. So now so this formula is used whenever, so the change of base formula is used to evaluate a log with base other than 10, other than base 10. So to evaluate the log with base other than 10, the base of the log has to be changed, right? You need to change the base. So the base of the log has to be changed 10. To base 10. And that's why we are using the change of base formula. For example, if you were given, that's the example, the one we just did earlier, if you're given log 6, so log 2 to the 6th, the base is not 10. we are in principle applying that rule. Let's see how that formula, can prove that formula. So let's consider, all right, y equals log b x. See that, well, this is here. Okay, let's consider it for a moment. Remember what we did in the first case here. We have our log. We change that in exponential form. So we'll use the same strategy here. So we're going to write this now, write in exponential form. So if we write it in exponential form, what we'll have, this is your base, that's your exponent, becomes b to the y is equal to x. So this is an exponential form. So I'm changing my log, right, to exponential form. So here we have now the next step, what we did for this part here now, once we have an exponential form, we took the common log for both sides. So that's exactly what we'll do now. Next, we're going to take the common log of both sides. Remember, the common log is base 10. So that we have it, we have log b to the y log x. Remember 10, it's there, but we know it's base 10, so we don't write it there, but it's understood to be there, base 10. Now apply the power law this side here. So now we apply the power law. So you can say apply. So what do we get? We have y log b equals log x. Now we can solve, right? In this case, we're looking at solving for y by dividing, so that we solve for y. So we divide both sides by log. So I have y log b is equal to log x. So y is equal to log x over log b. Now these are all base 10 still, don't forget that. Now, it looks familiar, right? So we have 10 here. So now, what did we have at the beginning? We said y is equal to log b x. So I will substitute now log b x for y, because that's what it is. So now we have log px is equal to log x. And that is our change of base formula. So it works for any log other than base 10. So let's apply this to a couple of questions. Here we have, to approximate the value for each log, then there's thousands. And we're asked to write them in related exponential form. So we'll apply this log rule here. So we say log x is log x over log b. So now this will be your b and that will be your x. So we have log, so 100. This will give us log 100 base 10 for log 6. And this I'll go to my calculator. And log 100 divided by log 6. It gives me 2.57019. So it's 2.570. So we can say log 6 to the 100 is equal to approximately 2.5701. Well, let's set it 1,000, so we can leave it to 0 there. So now to write it in exponential form, we can say 6 to the approximator, so we can be 6 to 2.570 is approximately 100. Next, we can go straight and we say that it's going to be log 32 equal to log 2. So use calculator for that. And so we have log 2 divided by log 3, 0.63. So we conclude that log 32 is equal to 0 approximately 0.6309. So we write it in exponential form. It will be 3 to the 0.6309 is approximately equal to 2. Just applying the change of base formula. So we apply the change of base formula. Which is this guy here. So there are a few questions in your assignment booklet, because that was covered in the lesson 5, change of base formula. Okay, we're going on to example 3. Now this is where we will be applying transformation formula. Now, let's review that formula for a minute here. So if you're given any kind of logarithmic function and transformation, it's similar to what we have done before in transformation. Here you have y minus k, or it could be written as, let's use a pen here, as y is equal to c log a d into x minus h plus k. And if you were to assimilate it, now this, your k, is the vertical translation. So up or down. Your h is a horizontal translation. The d refers to the horizontal stretch of 1 over d. So we have a horizontal stretch. So your c refers to your vertical stretch by a factor of absolute value c. Now, if the c is negative, then you have a reflection along the x-axis. And if the d is negative, you have a reflection along in the y-axis. So this negatives refer to reflection. So k is your translation. H is your translation, horizontal, so vertical, horizontal. C would be your stretch, a vertical stretch, and D would be your horizontal stretch by a factor of 1 over D. Don't forget that. So here it's written. So a general transformation then, if you have a log function of xy, so if it's transferred, you look at your transformation graph and your d is the x over d, so whatever d is here, replace it plus the h, if there is an h. Sometimes there's no h. For the y transformation from y equal to log b of x transform to the y will be c, whatever c is. If it's more than greater than 1, it's 1 times whatever the y value of y here plus the k. So it could be negative or positive. Okay, let's apply this here. It's a quick review to this question here. So they ask you to create a table of value for the graph y equal to log 3x. Now, it's very difficult unless you have to work through each one of these logs and change it to a base 10, or you have a calculator. It's very difficult to work it out that way. So the easiest way is to change the log form to exponential. So the first thing you want to do here is to change this, right? So to create a value, we're going to create a table of values for y equal, and to create a table of value for y equal log 3x, we write it in exponential form. So now if you write that in exponential form, it becomes 3. So 3 to the y is equal to x. So that's critical because it makes life very easy for you when you're doing your calculations. So I went ahead and created a table of values here, and I've changed, this is y equals log 3x. So I changed it to an exponential form. So this is what is given. So that's in exponential form here. By doing that, I will be able to develop a table of values for y equal log 3x. Once I have the x and y values for log 3x, that is transformed. Now, the reason someone may ask, okay, why am I using log 3 to the x? Now, if I were to strip away the transformation here, this is my horizontal shift, which is to the left 6 units. And so actually not to the left 6 units, but you need to change this equation for us. This becomes log 3. We factor out 2, x plus 3. So don't forget that we need to factor out. So this a shift of 3 units to the left. We have a horizontal compression of a half. But before I go on to the transformation, let's create a table of values for y equal log 3 of x. So we've established we can change it into an exponential form. Now, what is easy for you to do, because it's a log function, select the values for y. Then it's easy to find the value for x, because x here is 3 to the power y. So whatever the y value is, we can find the x value. Normally we have the x values first and then find the y value, but in this case it worked out that it's easier to find the y value. Select the y values, and then you'll use it to find the x values of the coordinate. So if you look at the first one here, the x is -2. Sorry, y is -2. X would be 3 to the -2, which is 1/9. Next one will be -1, so we have 3 -1, which is 1/9. Remember, it's 1. And now 3 to the power 1 is going to give me 3, and 3 to the power 2 is 9. So this is my x coordinate now. So this is my x coordinate. And this is my y coordinates. Now, here's my transformation. And by the way, you need to factor out if a common factor here would be, in this case, would be 2. I factored out that common factor 2. So it leaves me with 2 into x plus 3. You need to do that because you will not get it's more difficult. You need to do a mental map to find the transformation in terms of horizontal and then the compression. So using the transformation, you have x and y. So you have x over d plus h. This is your x coordinates for your transform, and this is your y coordinate points. So from our equation here, we have y is equal to log 3 to x plus 3. You have the d, this is your d here, is equal to 2. The h is negative 3 because it's positive, because you're going to the left, so h is negative 3. Your c is 1. Now, c is in front here, is 1. And the k, there's no horizontal shift, so the k is 0. So substitute these values into our transformation. We have x over d is x over 2. That's what I got here. Plus h, in this case, is negative 3. So my x coordinate would be x over 2 negative 3. Remember, I'm using, going back here. And this applies to all transformation, by the way, we've used before. Because I'm looking at this graph initially, and then there is transform. And the y, c is 1, and k is 0, so it becomes y. So there's nothing, no change there for the y. But before I go on to doing a transform graph, let me just sketch this graph here of the original y equal to 3. Oops, here we go. Now I'll sketch this graph here, y equal to log 3 of x. So let's go ahead. So these are my coordinates. So x is 1/9, which is about approximately here, and y is negative 2, somewhere here. Then we have x is 1, this would be 1/9, it'd be 1 over 3. Oops. Should be 1 over 3. Okay, correct that. And about here. And then x is 1, y is 0. That's expected. So we know that's from our general log function. The x-intercept is 1, 0. Next we have 3, 1. And then 9, 2, which is about here. So I'll go ahead and nice smooth curve as much as I can. So this is y is equal to log 3x. So we have our graph established going from, I think it's not curving backwards, it's going towards the asymptote, which is the y-axis. Now we go ahead and find our x and y coordinates for a transform graph. Now this x over 2, which gives me, so a little calculation going on here. Now, by the way, y is established. Okay, y hasn't changed because it says here, whatever y is, it didn't change from our transformation here because it becomes y itself. There's no, if you look at our graph for this here, there's no vertical shift, but there's a horizontal compression of a half. So we can say that here, horizontal compression, 1 over 2. And then we have a horizontal shift. of -3. That's what we have here. So what it's telling us now, this graph should be shifting 3 units to the left. Then you have a compression. There's no reflection, there's compression. So let's go ahead and work this out. Here we have the first one. This is where you have to use your wonderful calculator. So we have x is 1/9 over 2, so we have 1/9 divided by 2 minus 3. Now this worked out to be -53 over 18. I'll work it out. So 53, this works 53 divided by 18, or 2. So this is -2.94 approximately. It's approximately 2.94. Next would be 1/3 divided by 2 minus 3. So that's going to give us what? So we have 1/3 divided by 2 minus 3. Let's see what that will give us. 2.83 negative. So -2.83. So -2.83 approximately. So we just approximating it. And the next would be 1/2 minus 3. It's an easy one to work with. -2.5. 0, so point. Next we have x is 3/2 minus 3. That'll give us a positive value. Well, this is still negative here. We have 1.5. So we have 3 divided by 2, so 1.5. So -1.5 here. And the last one we have is 9 divided by 2 minus 3. And that will give us a 9 divided by 2 minus 3, give us 1.5. So these are our coordinates now for our transform graph. So we'll x and y, just to highlight them. I'm sure I can follow these clearly. So our first point now, by the way, let's look at our horizontal shape, -3. Right? So what did it tell us? It tells us our asymptote here, the first one, was y is equal to 0. So if it shifted 3 units to the left, our asymptote now for the transform graph would be y equals -3. So y equals -3 is our asymptote. So we have our asymptote. Maybe I'll use this might highlight it. So that's my asymptote. y equal -3. So my graph will not cross -3. So let's look at it now. We have x is -2.94, which is approximately here. Y is -2. X -2.83, which is about here. X is 2.5, y is 0. So now that's our x-intercept. X is -1.51, so 1.5 is about here. So we have a point there, and x is positive 1.5, so we're here. Y is 2. So our graph looks like we go on for a while here. So y is equal to log 3. You can write it as the original function. So this is my transform. So from our graph, we look at here, it said identify our question, part C now. Identify the intercepts, the equation of the asymptote of the graph, domain and range. So let's look at each part here. So the first thing from the graph, so we can write what we found, the x-intercept, it's -2.5. So this is our x-intercept. So let's look at the first one here. So A, x-intercept -2.5. Kind of redundant to write 0, but I'm just putting it in just for emphasis. Now, we'll look at finding the y-intercept in a minute, but let's look at the domain. So the asymptote here is y equals 0. So is y is equal to -3. So -3 is for a transfer. Y equals 0 is the asymptote for the original y equal to log 3x. The domain and range, so the domain, because our asymptote at -3, so our domain makes it that x is greater than -3. And the range, so -infinity to +infinity. You can write this, or you can say -infinity to +infinity. Or if you want to write this as -3 to infinity. Now to find a y-intercept, for the transform. Now, if you go back to this graph here, if we let x be 0 in this equation here, we'll end up with log 3 to the x. So let's look at that part here. I'll do it on a separate page. Oh, probably do have enough space here. So let's look at, let's say this is the original equation here. So we want to find the y-intercept. Okay. Let x equals 0. Right, and solve. So that equals 0. Just say from y equal log 3 to x plus 6. And solve. So if you let x be 0 here, so this would leave us to with, so that give us y is equal to log 3. Now this 2 times x is 0. 2 times 0 is 0. So that'll give me 6 here. Now we can apply our base law of change of base, or change of base formula. So that would give me log 6 over log 3. And I go my calculator, use calculator. Use calculator. And my answer is 1.6309. So this is your y-intercept. So we found our y-intercept, we found our range, domain, asymptote, x-intercept. Okay, so let's recap what we've done today. Our goal was to use the change of base formula to determine the value of a log and sketch a transformation of a graph, transformation graph of a log function. We developed or we proved change of base formula, and we've completed 2 examples using the change of base formula. And then we completed 1 transforming the graph of a log function. So your task before the next lesson is to complete questions 1 and 3, check your understanding. So try and complete these 2 questions on page 402 and 403, and questions 3 and 4 on page 405. The next lesson, we will be looking at examples of the change of base formula and examples of sketching transformation graph of a log function.